Hello everyone, welcome to my channel Essentials of Electronics. In today's video, we are going to discuss few other applications of op-amp. Yes, the first application now is I'm going to tell you something about voltage to current converter. Yes, voltage to current converter, how an op-amp converts the voltage signal into current parameter. So this kind of conversion done by the operational amplifier, the op-amp is called as transconductance amplifier. This transconductance amplifier. Yes. So the voltage to current converter, we have two different circuits. One is by connecting floating load, we can convert it. By going for grounded load, we can convert it. In many applications, we need to convert the voltage signal to its proportional output current. So operational amplifier plays a very important role. Yes, for this conversion. Now we'll first go in for floating load. Yes, a resistor with the feedback resistor in parallel connected to the op amp's output. An input signal is given to the positive terminal of the op amp. Yes, so this ZL, this ZF, R1, IL flows through this, IL current flows through this ZL. We let this terminal be A for the purpose of analysis. And hence, IL will be flowing through this. VI is the input voltage. IB current is approximately 0. Now, for this circuit, VI is equal to IL into R1 as the bias current is equal to 0. Therefore, IL is equal to VI divided by R1. So we have obtained the current in terms of voltage. IL is proportional to the input voltage and it is controlled by R1. Thus, it acts as a voltage to current converter. By floating load. Yes. Now I have another circuit to show the voltage to current converter with grounded load. Yes. So resistors connected in this manner fed to the op amp. Yes. Resistors connected this manner with a grounded load. Input voltage and the output voltage is collected over here. Terminal is grounded. R and R. V1 is the input voltage. ZL is the grounded load. Input voltage is fed through this. Input current IA flows through the R resistor. The total current IB, the bias current is 0. So here the value of because of this some current I2 flows in the circuit. It's a grounded load. So IL will be equal to VI divided by R. Thus, the operational amplifier is acting as a voltage to current converter using floating load and grounded load. So, the total current I1 plus I2 will be equal to the load current, which is equal to VI minus I1 plus I2 is equal to IL, which is equal to VI minus V1 divided by R plus V naught minus V1 divided by R is equal to IL. So on simplifying, Vi plus V naught minus 2 times of Vi is equal to IL into R, and VL is equal to V1 plus V naught minus IL into R divided by 2. Yes, this is the output voltage expression in terms of current expression. And next we'll move on to current to voltage converter. Current to voltage converter. So we called voltage to current converter as transconductance amplifier, isn't it? The current to voltage converter is called trans resistance amplifier. Yes, trans resistance amplifier. So what are the applications of this is photocell, photodiodes and photovoltaic cell give an output current that is proportional to incident radiant energy or light. The current through these devices can be converted to voltage by using a current to voltage converter, and therefore the amount of light or radiant energy incident on the photo device can be measured. So using op amp we can make a simple modification and convert it into current into voltage converter. Yes, I will draw a simple circuit of a current to voltage converter. A current source in parallel to the current source II, resistor, a feedback resistor, and a capacitor will be acting as a trans capacitor. This potential is at VB, VB, both same potential. RF is the feedback resistor and IF is the feedback current. The output voltage V naught is equal to minus II into RF. This is the output voltage. Hence, the output voltage is in terms of input current. The negative terminal is at virtual ground. The current II flows through the feedback resistor. Thus, the output voltage V0 is equal to minus II into RF. This may be pointed out. The lowest current that this circuit can measure will depend upon the bias current of the op amp. This means that the IC741 used here can be used to detect lower currents. The resistor RF is sometimes shunted with the capacitor CF to reduce the high frequency noise and the possibility of oscillations. Here the input current, source current is converted to the, it is connected to the inverting terminal. I will draw another circuit to show the input source current being connected to the non-inverting terminal and how do we do that current to voltage conversion. RF resistor being connected to the output positive terminal R1, the input current II, the input voltage Vi, the input, this is RF resistor, the input voltage Vi is equal to Ia into Ri. The output voltage V0 is equal to 1 plus RF divided by Ri into the input voltage, which is equal to 1 plus RF divided by Ri into, we know Vi is equal to Ia into Ri. Therefore, V0 is equal to 1 plus RF divided by Ri into Ia into Ri. So the output voltage we have got in terms of input current. Thus, the op amp is acting as a current to voltage converter. This is a trans resistance amplifier. So the voltage, so what are the previous circuits we have now discussed? So far as voltage to current converter in two different modes with floating load and grounded load we have discussed. Then current to converter with the input source current fed to inverting terminal and non-inverting terminal we have discussed. The next topic is integrators and differentiators. Integrator. What is an integrator? The output voltage will be the integral value of the input voltage. So we are going to obtain that using an op amp circuit. A capacitor being connected to the feedback path of the op amp. Yes, the other terminal being grounded, input signal fed to the inverting terminal. B in R1, IA flows here. IF is the feedback current, C is the feedback capacitor, and V0. So the input current IA is equal to IF is the same current as that of the current passing through the capacitor, but we know that IC is equal to C into dV divided by dt. So V in minus V2 divided by R1 is equal to CF into d by dt into dV is equal to V2 minus V0. Since V1 and V2 is equal to 0, then V in by R1 is equal to CF into d by dt into minus V0. The gain decreases with the increase of frequency. Hence, now the output voltage is an integral value of the input voltage, thus acting as an integrator. So integrating on both sides, we will be getting Vn by R1 into dt is equal to integral of Cf to d by dt of minus V naught into dt, which is equal to Cf into minus V naught. Therefore, V naught is equal to minus 1 by R1 Cf integral of V in dt plus C, where C is the integration constant and is proportional to the value of the output voltage V naught at time t is equal to 0 seconds. For example, if the input is a sine wave, the output will be a cosine wave. If the input is a square wave, the output will be a triangular wave in the case of the integrator. When Vn is equal to 0, the it will be working as an open loop amplifier. This is because a capacitor connected in the feedback loop acts as an open circuit. Then the capacitor reactance is equal to infinity is set to the input offset voltage Vi. In other words, the input offset voltage Vi naught and the part of the input current charging capacitor Cf, the Cf will produce a error voltage at the output of the integrator. Therefore, in a practical integrator, in order to reduce the error voltage, a resistor RF is also connected across the feedback capacitor. Across the feedback capacitor. So the stability can be obtained. Frequency is given by F is equal to 1 by 2 pi R1CF. Both the stability and the low frequency roll-off problems can be corrected by the addition of a resistor RF. See, in the feedback path, we had connected a capacitor. So, because of stability issues, yes, we can connect a resistor in parallel with it. Yes, so that the frequency response of the practical indicator is shown as follows. Then the ratio of RF by RI will be constant. However, after a particular frequency, the gain will decrease at a rate of 20 decibels per decade. Yes. So if we take frequency log scale and gain in decibels. At initial frequency, this is the frequency curve, and it will, as the frequency goes on reducing, the gain will also decrease. Yes. So this, in an ideal integrator, this is a curve obtained in an ideal integrator circuit. This is the point at which RF and R1 are the same. So RF R1 minus 3 decibels will be approximately at this frequency called the resonant frequency. So F is equal to 1 by 2 pi RF into C1, and this frequency is a maximum frequency. FB is equal to 1 by 2 pi R1 C1. Yes, where the gains value is modulus of V naught by Vi. This is the frequency response curve. For an ideal integrator, we will be getting this curve. For a lossy integrator with the losses. Yes, lossy integrator. We are getting this practical curve. This curve is a practical curve. So in an integrator circuit, if a square wave input signal is fed in this manner, the output which is obtained will be of this. Thus, it can convert a square wave into triangular wave. Yes, square wave. We can draw vertical lines like this and show the output of the integrator. Yes, triangular waveforms are generated in this manner. So in this video, we have seen another voltage to current converter, trans conductance amplifier, current to voltage converter, trans resistance amplifier, and integrated circuit using op amps. Thank you.